All right. Yeah. So thanks a lot for the invitation. Yeah. So yeah. So over the past few years, I worked on my PhD, where I focus on the optimal delineation of agricultural parcels from satellite imagery using the multi-resolution segmentation algorithm. So today I'm going to present what I did in the PhD. So my name is Gideon Tetteh, and I'm working for the Thünen Institut of Farm Economics, here in Braunschweig, Germany. So a brief history about Thünen Institute. So basically, Thünen is a German federal research institute, and we have three main thematic areas we focus on. So rural studies, forestry, and then fisheries. So a couple of years ago, the Thünen working group, the Thünen Earth Observation Working Group was formed, and what we are doing mostly is to explore the use of satellite data in order in those three thematic areas. So here you have a beautiful picture of the Thünen Institute in Braunschweig. So the big picture is so I mean the overarching goal is to create a German-wide object-based crop type map from satellite images. So here is an example of a Sentinel-2 image somewhere here in Germany. And here is a corresponding agricultural parcels extracted through image segmentation. And here is now the corresponding object-based crop type map created from the segments. So so the question is, I mean, how useful is an object-based crop type map? So I mean, of course, it can be used in in the accurate computation of the areas of different crop types. And it can be used also in computing landscape metrics for biodiversity assessment, and also for monitoring different agricultural policies. So, for example, in Europe, we know about the common agricultural policy, and of course, there are many more things you can use this data for, be it crop modeling or crop rotation analysis. And I mean, it's been shown in the literature that the quality of image segmentation has a direct impact on the corresponding crop type map. And I think today, we saw some examples already. So in my PhD, what I focused on was the optimal segmentation of agricultural parcels from the freely available Sentinel-1 and Sentinel-2 images. So for the study area, I focused on Lower Saxony, because at the beginning of my PhD, I had reference data readily available for this area in the form of the agricultural parcels in the geospatial aid application as part of CAP. So to ensure efficient segmentation, I divided Lower Saxony into 10 by 10 kilometer tile grids. So when it comes to segmentation, of course, there are different methods one can use here in the literature. I think it's a lot. So here I selected the multi-resolution segmentation. So in short, MRS algorithm in e-cognition. So a review paper in 2017 showed that almost 81% of researchers use this particular algorithm, and then in 2021. About 65% of 125 papers use this algorithm, and then I mean its superior performance to other algorithms. I mean it's quite it's well demonstrated in the demonstrated in the literature. So we all know, I mean, to use the MRS algorithm in e-cognition, there are three main parameters one would have to set. So the first is a scale parameter, which is a free parameter, which is used by the algorithm as a termination criterion, and therefore, it determines the average size of segments. And then we have shape, which ranges between 0 and 0.9, and then we have compactness, which is between 0 and 1. So then the question is, I mean, what is the best combination to use to segment, any feature, or in my case, to segment agricultural parcels? So then comes the question of parameter optimization, and the traditional approach to parameter optimization is grid search. So grid search basically is a very exhaustive search, doing all manner of possible combinations, and it tries to identify the combination which is the optimal. So of course, it is quite inefficient. But a more advanced approach is a Bayesian optimization, which is more efficient and then it's more effective. And so, I mean, Bayesian optimization, the idea is, I mean, it tries to make new predictions based on previous model evaluations. So in my thesis, I use Bayesian optimization. So here is an example of a grid search. So here I use 31 scale values, 19 shape values, and then 21 compactness values. So in combination, we are talking about more than 12,000 parameter combinations. So it took 11 days to run, and then the best result was achieved. The best combination obtained an accuracy of 68.83% here. But now, if you compare to Bayesian optimization, it took only 16 minutes to run using only 150 parameter combinations, and the best combination produced an accuracy which was even higher than grid search. So, I mean, this tells you about how efficient Bayesian optimization is. So, in my thesis, I had 3 main objectives, and each objective corresponds to a paper. So the first was to develop a supervised Bayesian optimization approach for optimizing the MRS parameters. And the second is to develop an unsupervised version of the first paper. And then the third was to identify the optimal feature set for segmenting agricultural parcels. So an overview of the methods I use. So it begins with the first paper. So based on using the tiles and then Sentinel-2, the visible and near infrared bands. So I clip the Sentinel-2 images to the tiles, and then I mask out all non-agricultural areas. And then in combination with the reference data, I was able now to create the supervised approach. And then in the second paper, using the same input data sets from the first paper, I created the unsupervised version, and I did a comparison between the first paper and the second paper. So in the third paper, so here I used Sentinel-1 and Sentinel-2 using monthly bin composites. The same procedure, so clipping the images to the tiles and then removing non-agricultural areas, creating some feature sets, identifying the optimal feature sets, and then finally segmenting the agricultural parcels in Lower Saxony. So Bayesian optimization, of course, there's a lot of mathematics behind Bayesian optimization, but here the idea is to just introduce the basics. And to use Bayesian optimization, there are 4 main things one should define. So the first thing is a domain space, which is simply the space for each parameter within which to find the optimal combination. So for scale, I use values from 20 to 200, shape from 0 to 0.9, and then compactness from 0 to 1. And then the second thing to define is an objective function to optimize. So in my case, it is simply a function that takes a combination of scale, shape, and compactness, and then it returns a scalar value that represents the segmentation quality. So I'm going to come back to segmentation quality in the next slide. And the third thing to define is a so-called surrogate model, which is simply initialized by evaluating some user-given combinations. So in my case, I used 125 initial combinations, which I gave to the algorithm. And then finally, there's an acquisition function, which simply is used now in sampling new parameter combinations with the highest probability of optimizing the objective function. So in my case, I sampled 25 new combinations. So back to segmentation quality. So there are 2 ways you can measure the quality of segmentation. So the first, is supervised, which is the first paper. So here I use the reference data. So in this case, the GSAA parcels to calculate the geometric match between the segmentation and the reference data. So here I use the well-known intersection over union metric. Now, the second approach is to do it unsupervised. So here there's no reference data. So what you have to do is to use the image content to measure the level of accuracy of the segmentation. So here I use a combination of variance, which I use to measure the intra-segment homogeneity, and then spatial autocorrelation, which are used to measure intersegment heterogeneity. So here is a bar chart, showing the segmentation accuracies of the unsupervised optimization, and the blue bars, and then the supervised optimization, which are the orange bars. So on the x-axis are some selected tiles, and on the y-axis are the corresponding segmentation accuracies. So overall, what you can see is that the supervised approach performs better than the unsupervised approach, which is quite understandable because here we are using reference data here during the optimization process. But here I highlight T2, where, as you can see, there isn't a very strong, very significant difference between the two approaches. And then T17, where there's a very big difference between between those two approaches. So here I show already for T2. So over here I have the Sentinel-2 image for T2, and here is the corresponding supervised results, and here is the unsupervised result. So each segment here and here is colored by its corresponding match to the reference, to the corresponding reference parcel in the GSA, and the interpretation of the colors you can see over here, beginning from 0 to 100. So the brighter the color, meaning the better it's matched to the reference data. So, but visually, what you can see is that those two results are not so much different here. And the reason you can see from the Sentinel-2 image that here the fields here are very small and very elongated. So of course, Sentinel-2, the spatial resolution of 10 meters, is unable to properly resolve those fields. But if you look at T17, where the parcels are a bit bigger, here you see a bit more of differences here visually between the supervised and the unsupervised. In the supervised, you see a lot more yellow colors, which is an indication of a higher accuracy as compared to the unsupervised approach. So my conclusion from the first two papers is that supervised Bayesian optimization, performs better than the unsupervised approach. But in cases where there's no reference data, then the unsupervised approach is obviously inevitable. Therefore, I would say those two methods I developed are complementary to each other. And now, if like moving to the to the last paper, so here I had three main objectives. So the first thing was to identify the optimal feature set for segmenting agricultural fields. The second was to analyze the accuracy at which different fields can be segmented throughout the growing season. And the third is to assess the accuracy that can be achieved for different field sizes. So for this particular paper, I used monthly mean composites from Sentinel-1 and Sentinel-2. So I created several different feature sets, and then I realized the optimal combination I found was the combination using 6 optical and then six and then 2 radar indices, which I named S2, S1I. And then so based on this particular feature set now, I created 8 incremental data sets. So it begins from DID1, where I use only the feature sets of March. DID2, where I use the feature sets of March and April, and then DID8, where I use all the feature sets from March to October. So for example, at DID1, it's going to contain only 8 bands. So 2 optical and then 2 radar. So only 8 bands. But at DID8, it's going to contain 64 bands. So 8 months times 8, so it's 64 bands. So yeah, again, I showed box plots, highlighting the distribution of the segmentation accuracies over some selected test styles. So yeah, as you can see, at the beginning of the growing season, the lowest accuracy was achieved. But then as we get to the end of the growing season at DID8, the highest accuracy was achieved. And this, again, is quite understandable, given that for agricultural parcels, you need multi-temporal data to be able to properly characterize the phenology of the different land uses. So based on DID8 now, I was able now to segment all agricultural parcels in Lower Saxony. And then based upon that, I went the next stage now to compute the accuracy that can be achieved for different field sizes. So on this column, you have the field sizes, and on this column, you have the corresponding segmentation accuracy that could be achieved. So from very small fields to large fields. So as you can see, in general, as the sizes of the fields become bigger, the accuracy also increases accordingly. But interestingly, the highest accuracy was achieved for medium fields. So then I tried to figure out why this happened, and I found some two examples why this happened. So first is an issue which is caused so over-segmentation, which is caused by the presence of hedges in the image. So here, the black outline represents the parcel which is declared by the farmer in the GSA. So this farm is used to grow potato with a size of 20 hectares. But after segmentation, you can see there's B1 here and then B2. So two different segments were created. And this is because in this particular field, the farmer has allocated some area as hedges. So I mean, within the CAP framework, if farmers want to access the greening payments, for example, and there are more than 15 hectares of land, they must dedicate at least 5% now to ecological focus areas. And this is the case of this particular farmer. And so this is the reason why the accuracy is low for this particular field, because you have two different segments created instead of one. And here is a over-segmentation, which is caused by non-optimal parameters. So here again, this particular parcel is used as a mowing pasture, and the size is about 16 hectares. But after segmentation, as you can see, again, two fields have been created, so B1 and then B2. And this is purely because this particular field is located in an image which is more dominated by smaller fields. And this is the reason for the over-segmentation here. So what are some of the potential uses of the segmentation? So the first thing would be to verify the farmer's declarations within the CAP framework. So for example, here is a declaration in a red outline by a farmer. But after segmentation, 3 different fields were created. So CS1, CS2, and then CS3. So through segmentation, we are able to tell where there are some inconsistencies in the declarations of farmers. But it's important to say here that this to be sure or to be more conclusive on whether there is some non-compliance or not, one must go a step further now to do agricultural land use and activity. To identify the agricultural land use and activity existing on those segments. So a second potential use is crop type mapping. So here on the left side, you have a pixel-based crop type map, which was produced as a collaboration between Thünen, Humboldt University, and then Ländliche Institut. So I overlaid my segments on it, and then I did majority voting to produce the object-based crop type map here. So here, as you can see, the salt and pepper noise in this image has been removed from the object-based crop type map. But more importantly, the accuracy increased from 78% to 81% in the object-based crop type map. So conclusions from the third paper is that Sentinel-2 generally yields better results than Sentinel-1 for segmentation, but the combination of Sentinel-1 and Sentinel-2 improves segmentation accuracies, and multi-temporal data is key to optimal segmentation. And then Sentinel-1 and Sentinel-2 are more useful for segmenting medium-sized fields, and aggregation of pixel-based maps with the segments can improve classification accuracies. So my general conclusions are that optimal segmentation requires optimization of all parameters, and the input data must be optimized as well. And then the parameters which are established can be used in segmenting agricultural parcels in different years. And then so as a future research now, I'm focusing on comparing my supervised approach to state-of-the-art deep neural networks. So this is ongoing now, and I'm working on the paper on that. And then finally, is to evaluate higher spatial resolution images. So for example, PlanetScope for segmenting small and then very small fields. So yeah, thank you so much for your attention, and then I'm ready to answer some questions.